Okay, so today we're going to start the unit on vectors, unit 8, and it's blurry. Let's see if I can get it to focus a little bit more. There we go. In the real world, some quantities can be represented by real numbers like temperature, distance, area, volume. Other quantities, though, like force, velocity, acceleration, require not only a number to represent them, but also a direction that they are being applied to. We can represent these types of quantities with what is called a directed line segment, or what will become a vector. So what is a directed line segment? A directed line segment has what's called length, magnitude, and a direction. So here's kind of how it looks. So here's the initial point, P. It has XY coordinates. Here's the terminal point, Q, XY coordinates. And we are going from P and ending at Q in that line of direction, as the arrow indicates. This is a directed line segment. It has a length and it has a direction. I want you to write a directed line segment like this. It's PQ and a one barbed arrow on top. Okay, this indicates our directed line segment / vector. Your book uses a full arrow. I don't like this because this full arrow is the symbol for a ray from geometry days. An array has a starting point, but there is no end point. It goes on forever. Okay, so I don't like that form. Please don't use it. Use the one barb form for a directed line segment / vector. The magnitude, which is the length of this vector right here, is indicated using absolute values around it. Absolute value, remember, means the length or the distance between two things. And so this means the distance between P and Q. Okay, that's the magnitude, the length of the directed line segment. Any directed line segments with the same direction and magnitude are equivalent. And that's important because that was what allows us then to start talking about what's called a vector. The directed line segments are everywhere. You can kind of think of like the wind. The wind is blowing, and it's blowing all over the place, and these little lines are going everywhere. These little directed arrows are everywhere. And so how do I indicate, all of them at once? Well, every one of those things that have the same direction and the same magnitude are what are called equivalent. And because of that, then I can start talking about this thing called a vector. A vector is the directed line segment that represents all equivalent directed line segments. Good. Okay, so where the initial point is at the origin and the terminal point is at some value AB. So vector V, to indicate it as a vector, instead of saying AB is a point with curvy brackets, we use these little pointy brackets. And when you see those brackets, it means this is a vector, and that is the terminal point of the vector, and the initial point is at the origin. Okay? Since all directed line segments that have the same direction and the same length are equivalent, then we use this vector, which is in standard position, represents all of those in the entire coordinate system that have these exact same parameters. The angle that we are traveling, so the direction angle is theta. The terminal point is AB. The initial point is 0, 0. This is a vector drawing in standard position. So how, if I'm given a directed line segment where any 2 points can indicate it, how do I change from a directed line segment to the vector equivalency? So we know what the vector is here. And so here's how I change the directed line segment to component form. This, by the way, is component form. You just simply take the endpoint, the x values, subtract them, the y values, subtract them, and you will have the vector V. Very simple. So remember, even though it's a directed line segment, it is also a vector. It's just not the representative vector that we're going to be using quite extensively. So how do I find the magnitude of a vector? Since the magnitude means the length of the vector, I can just simply do Pythagorean theorem, because if you look at this picture, I can drop this down, and this would be A and B, and I have a right triangle then, and then Pythagorean theorem applies. This is the vector object. The magnitude would be the length of that vector. So the length of this vector is A squared plus B squared and the square root of that, Pythagorean theorem. Also in this right triangle, A and B would be here. I have this angle right here. I can use the tangent function as B over A to find the direction angle of my vector. So this is how you would find those two pieces of information when you're given a vector in standard form. There's a vector called the zero vector. Zero with the vector symbol on top is the zero vector. And then it just basically is that represented as 0, 0. This is a vector that has no direction and zero length. So initial point, terminal point is the same point, so there's nothing going on there. But it is there mathematically, they use it. I did forget to mention here that when we talk about vectors in your textbook, they're not going to have these little symbols across them. They're going to have a bold-faced letter. Okay, but since we can't write in boldface, we use the vector symbol on the top to indicate it. So when you see a bold-faced letter in your textbook, it represents a vector name. What is a scalar? A scalar is just a number. Okay, it's just a number, and so I can't remember why they call it a scalar. So what is vector addition and scalar multiplication? Well, I'm going to take two vectors, and k is going to be my scalar. It's going to be a real number. And so to add vectors together, you simply add the start coordinates. So the x coordinates here, add together, the y coordinates, add those together, and you'll have your new vector. Scalar multiplication, k times some vector, you just multiply k to each of the components inside, and that's how you do scalar multiplication. So let's look at a visual of this stuff so you can see what's going on here visually. So here's a visual representation of our addition and scalar multiplication. And this right here is going to help you with solving many problems that deal with different vectors and acting on the same object. So here's vector u, here's vector v, and this is vector u plus v. If you notice, because these vectors are the representations of all vectors of the same length and direction, and there's an infinite number of them throughout the entire plane, I can find one that is equivalent to this that starts right there and goes the same length and in the same direction as that, meaning that they are equivalent. They're literally the same. And I can do the same thing for vector v. I can find an equivalent one that starts right at that terminal point and goes over to here. What you see is we develop a parallelogram with the two vectors, and then the diagonal is the sum of those two vectors. The diagonal of the parallelogram is called the resultant vector, which means it's the vector sum. It's the result of the sum. So the result, they call it a resultant vector. It is the diagonal of this parallelogram. So this is how you can find the sum, by creating the parallelogram and then find that diagonal. Scalar multiplication just changes the length. So here is vector u. So if I want to know what 2u is, then here is 2u. See, it's in the same direction and it is twice as long. For the most part, when scalar multiplication, it does not affect the direction of your vector, except when it is a negative number. And if it's a negative number, it will go in the opposite direction. So a negative u is the same length as that one, but it's now going in the opposite direction. So that's what negatives do. Okay. What is a unit vector? A unit vector is a vector of length 1. A direction vector is a unit vector in the direction of a given vector. you'll be asked to do questions like this, and I'll show you here in a minute. So literally, here's what we have. Here's a vector u. If I take a vector v and divide by its magnitude, okay, that means I'm dividing the length out, and that length is becoming a 1. So that's what's going on here. This is, remember, this is a number, so this is a scalar. And what you're doing is you're reducing the length down to a unit vector, so a length of 1. So that means u will be a unit vector in the same direction as v. So it's going in the same direction, it's just not the same length. It's a length of 1. That's how I get a direction vector. Okay? So let's look at an example I have right here that we're going to do. Here's two vectors, v and w. And here is what I want to find. I want to figure out what this is. What is vector v plus 2 times vector w? And we're going to look at this in 2 different ways. We're going to do a visual representation of this, and then we're also going to do an algebraic. The visual, just so you can see how it works out, we don't usually do a visual representation except for a few times. Mostly we do the algebraic. So in our visual, we need to graph the 2 original vectors. And I'll just do a quick little shape here. So this will be 1 and -1 and -2 and -3. We're going to go by 2's up here. So 1, 2, 3, 4, 5, 6. So vector v is -2, 5. That means I start here and I go to -2 and 5. So that's about right there. And we draw that vector arrow. And this is -2, 5. That is vector v. This vector is 3, 4. So go over 3 and up to 4. Put a dot there. And then that is vector w. This is 3, 4. When I do the point here, I'm naming the point, so it's as a point, not as a vector. So what I want to do now is I want to find the resultant of this thing. I need to extend this out to 2 times. So if this is 1 w, then if I do the exact same length again in the same direction, then I have the other one. So when I do that, it's going to be out here at 6, 8. So in extending this right here becomes another w. So this right here is 2 times vector w. So this is the 2 sides. I can take this same thing, and you can kind of do rise over run to help you draw this out. So I'm going up 8 and over 6. So if I go up 8 from here, and then over 6, I'm going to be right about there. And so there is another 2 w's. This right here, from here to here, is another vector v. And so what is my result? That's where I'm heading. From here directly to there is vector v plus 2 times vector w. What is the name of this point? It's 413. So what is the name of this new vector? 413. That's how you do a visual representation. Okay? For an algebraic representation, I would start off by putting in the component form of each of these vectors. And then this is 2 times 3 fourths. And then you can usually do this all in one step, but I'll show you all the little one step at a time. And then I'll do the scalar multiplication here. So that's going to be a 6, 8. And then this is going to be a -2 plus 6 and a 5 plus 8. And a -2 plus 6 is 4, and a 5 plus 8 is 13. And so you can see we get the same answer algebraically. Let's look at the next one, same idea. So here we go. -1, -2, -1, -2, -3, 1, 2, 3, 4, 5. So W is 3, 4, 3, 4. V is -2, 5. So this right here would be -2, 5. Okay. So the difference here is that I can consider this to be W plus and then a negative vector V. Well, what does a negative do? A negative is the same length, just in the opposite direction. Okay? So I can extend that way down here if I wanted to. Okay? That's really what's going on. But for the sake of drawing here, I can also going to put it over here, right, to complete our parallelogram. So this can go down this way. And then we can also put one right here. So this is a -2, 5. So that means I can go down 5 and over 2. And so this right here, kind of missed it, but you get the idea. This is a negative V. This is the W, and this is the negative V. So see the parallelogram right here? So this, from here to here, would be my diagonal. What is the name of this point right here? Is 5, -1. This is W minus V. Okay? So algebraically, what is W minus vector V? 3/4, -2, 5, 3/4, and then distribute this out so this becomes plus 2, -5. So this is 3 plus 2 and 4 minus 5, 5, -1. Algebraically, visually. Okay? I have another one I want to do, and that is this one. We talked about the unit vector in the direction of another. So here is a vector W. I want to find a unit vector that is in the exact same direction as W. Okay? So we know that I'm going to need to find the magnitude of W. The magnitude is just a Pythagorean theorem where this is A and B. So it is the square root of 3 squared plus 4 squared. And that is the square root of 25, which is 5. And we only need the plus value because of absolute values of distance. So my unit vector is the vector that I'm using divided by its magnitude. The magnitude is 5, so that means this is a 1/5 times W, which is 3, 4. So then U, my unit vector in the direction of W, is going to be the vector 3/5, 4/5. This has a magnitude of 1, and it is in the same direction as vector W. Okay, so that's how those work. So other unit vectors. Your standard unit vectors. The vector of length 1 that is on the x-axis, we call vector I, and it is 1, 0. It is a unit vector, and it is the horizontal one. The vertical one is J. The unit vector 0, 1 is on the y-axis up to 1. That is J. all vectors can be put in this using this concept here, because all vectors then would be some kind of linear combination of these things. So vector v, which is AB in component form, can be moved into the ij unit vector form, which they call linear combination form. So A is that, B is that, bring out the A, so it's A times the unit vector I, and B times the unit vector J. That means A vector I is a vector in this direction of length A. B vector J is a vector in the length of B in this direction. The result of the sum of those two things, these two vectors, is vector V. So that's how we use the same vector but come at it from a different perspective. The linear combination format. You'll be given them, and this, you're going to be able to go back and forth. So literally, in vector component form, it's AB. In linear combination form, it's A vector I plus B vector J. You can literally just go right back and forth between the two. It's not difficult. Resolving the vector into its components basically means using the direction angle and the trigonometry to find the components of a vector. So how does that work? It works like this. Here's vector V. This is the length. This is the length. Here's the direction angle. Okay. Using trigonometry, the cosine of this angle is adjacent over hypotenuse. Well, the hypotenuse would be the magnitude of this vector, because vector V is the name of the object. Its magnitude is its length. Well, if I have that, then I can tell you what A is in this format. Likewise with B. So the component AB, A is the magnitude of the vector times the cosine of its direction angle. B is the magnitude of the vector times the sine of its direction angle. So then I can write it in trig form, if you will, of this vector. So vector V is AB in component form, and trig form, if you will, is this one. So all of these are equivalent ways of writing the same vector. And so we want to be able to transform back and forth depending on the information that we have. Okay? Velocity, the vector velocity of a moving object, is a vector because velocity has both magnitude, a length or a value, and a direction. Think of throwing a baseball. If I throw a baseball, I'm throwing it with some force, I'm giving some speed behind it, and a direction in which I throw it. The magnitude of the velocity is called the speed. Okay? How hard I throw it is basically the speed of this thing. All right? So I have another example I'm going to do with you. Find the components of vector V with the direction angle of 120 and the magnitude of 6. Okay? So how do I do that? Well, we just have the formula for it. Remember, vector V is the magnitude times the cosine of the angle of direction, and the magnitude times the sine of the direction angle. So I just need to plug this information into this format right here. So my vector V is going to be the magnitude times the cosine of 120 degrees, and the magnitude times the sine of 120 degrees. And then we need to work those out. The cosine of 120 is a negative 1/2. The sine of 120 is the square root of the square root of 3 over 2. And then we clean this up for a final form. Negative 3, the square root of 3. And so that's how we do that. The last example I have for this video is find the magnitude and the direction angle if I give you a vector. So here's the vector in component form. What is its magnitude? What is its direction? So again, the magnitude, of u is based off of the Pythagorean theorem. That's a and b, so it is the square root of a squared plus b squared. And that's a 9 and a 25, and 9 plus 25 is the square root of 34. So that is the magnitude right there. To find the angle of direction, it's important that you maybe just draw this vector out real quick. Just sketch it. -3, 5. It doesn't have to be perfect, or is over here. They're asking for this angle right here. This is the one I want. Okay? So the angle is in quadrant 2. To find the direction angle, you use this equation right here. The tangent is b over a, b. So then we have the tangent of our angle is 5 over -3, or -5/3. And when I take this thing and do the inverse tangent, so the angle I have in this equation right here, the inverse tangent of a -5/3, remember from inverse tangents definitions, this is going to give me a negative angle in quadrant 4. It's going to give me this angle down here. I don't want that angle. I want the one in quadrant 2, but we know that it's halfway across the circle from it. So our angle is this thing plus 180 degrees. That's going to give us the angle we want. Okay? And so when we work this out, we get 120.964 degrees. So there is my direction, and there is my magnitude of that vector u. I'm going to do a secondary video right now that has some additional examples to do. You want to make sure you watch it so that you can do some of the other, use it for helping you with some of the homework.